Very quickly, let's just continue where we left off last week. So last year when we did this, we kind of went in depth onto pretty much all of the different bins, all of the different topics related to this. This year we decided not to do that because we're really only testing a very small part of the heap allocator in the project, and we found that it can mostly just confuse people to hear about everything related to it, so we cut out a good part of it. It's still on the slides. The reading I linked last week, it also talks about it. If you're curious, I would highly recommend to go through those readings. Those are very good. But yeah, so we're going to very briefly go over the last few slides from the last lecture, but we're not going to go in depth them at all. So very quickly, so you remember the different bins, different linked lists for different sizes. There are the fast bins. Another slide on fast bins. Those are basically very, very simple data structures. They have the size field, a forward pointer, and a singly linked list for sizes between 0x20 and 0x80. They reside in the main arena in this area here. It's possible for them to be up to 0xp0, but in practice, it's an option in libc when libc is compiled. In reality, they're usually contained within this range, and the upper three size fields are not usually used, at least in the default Ubuntu libc compiled version that everyone's probably using. So that's the fast bins. The small bins are for a little bit bigger, for a bigger size range from 0x20 to 0x3FO. They act similar to the fast bins to a degree where they have one. In this case, it's a doubly linked list though, but each size in that range has one linked list to it. It's a doubly linked list in this case, where they have FD and BK pointers. Basically, just if the fast bins are full and it's still in this relatively small size range, you use the small bins instead. Then there's the large bins. These are much bigger, much more complicated. They have 4 pointers instead of 2. It's a doubly linked list of a doubly linked lists. Not going to say anything more about them, I think. If you're curious, the slide has some more information they're reading too. I'll upload this. Those slides are already uploaded. But yeah. And then there's the unsorted bin. This one is a little bit interesting to us, so I'll briefly explain it a little bit more. So when you have let's say you allocate a chunk of size 0x300, this is above the fast bin range and above it's above the fast bin range. Let's assume the T-cache doesn't exist in our example yet. We're dealing with an older libc version. So you make this allocation of size 0x300 and you free it. Assuming the T-cache doesn't exist, where would this go from the size range we talked about? So the other lists are the small bins, the fast bins, and the large bins. Anyone want to take a guess where a size 0x300 would go?
Large bins.
Almost. The large bins are size 0x400 to 0x80,000. But yeah, almost there with the small bins. Next time. So based on our theory, these would go into the small bins. However, Malk does it a little bit more complicated by using the unsorted bins. There we go. So when you free this, instead of immediately putting it into these small bins, it instead puts it into the unsorted bin list. The unsorted bin list is once again a doubly linked list, but this one, in this case, does not care about sizes at all. You can put any size in there, and it's just going to put the chunk into this list. So let's say you free this, it's going to go into the head of the linked list. You can free another chunk in that size range, maybe 0x200. It's also going to go in there. You can even chunks that would go into the large bin, the large bin and the small bins use this unsorted bin list. So an allocation of size 0x600, if you free it, it would also go in there. Then when you do an allocation, malloc is going to start traversing. So first, going to check the fast bins and the T-cache if it exists, if those can service the request. If not, it's going to start traversing this unsorted bin list. And basically, let's say this is the linked list, and you try to make an allocation of size 0x500. It's going to check the first entry. Is this big enough to service an allocation of size 0x500? If yes, it's just going to return it to you, and it's done. In this case, it's of size 0x300. That's not big enough. And so it's just, at this point, is when the allocator is going to sort this into the small bins. It's going to move on to the next one, 0x200. Also not big enough. Throw it in the small bins, move on to the next one. 0x600, this one is big enough, return it. Yeah.
So are things only sorted when some memory allocation occurs? It'll do it on the floor, kind of?
Yes, exactly. So I'm not exactly sure why they did that. To me, it kind of feels like it's something that makes free calls a little bit faster, but potentially makes malloc calls a little bit slower after a free has happened. That's what it feels like. There might be much better reasons for it that I'm not aware of. I didn't find any information on it, but yeah, that's how the unsorted bin list works. You're probably not really going to be using that one either, but I just wanted to explain it because that one's a bit weird. For all information on all of these, the readings I linked last lecture, you're not going to need them for the projects, but it's pretty interesting, in my opinion at least. I just don't want to go too in-depth in the lectures on this because I think it's just going to be confusing to people. So there's the T-cache. Are you guys any questions on this so far? What I just went over? Small bins, large bins, a bunch of linked lists for different sizes. Let's leave it at that. Then there's the T-cache bin. This one we will be using in one of the projects. So basically, it's a pretty recent addition to libc. Came in version 2.26. I think that was like 2016 to 2018, somewhere in that range. I think we're currently at version 2.36, so a bit further ahead, but it's not that old. So basically, as discussed last week, there's a limit on the concurrent arenas you have. And with a T-cache, basically every single thread has its own memory region or its own allocator region that it can use for free lists, so it doesn't need to like share the fast bins or the small bins with the other threads that might be using the same arena. So there's 64 of them of size 0x20 to 0x410, and they can hold 7 chunks per size field. So each one of those sizes, once again, singly linked lists like the fast bins, and each one can hold up to 7 chunks. Each linked list can be of length 7. So during allocations, the T-cache is going to be the first set you check, basically for the main reason that that is thread local. So if you have many threads, the T-cache is probably going to be the fastest, because if you have many threads, the small bins, the fast bins, all of these, since they're based on the arena, you might need locks to be safe from concurrency bugs. Similar to the fast bins, these are also not regularly coalesced. And let's pull up a demo binary for this. Let's go to the last lecture's things.
Oh, quick note. Project 3, Challenge 2, I just saw a CampusWire post. There's a bug in it. I asked you to explain why we can't do something naively. GCC optimized the check I had to make it harder, so that check just doesn't do anything anymore. So you can just talk about how you have to do a canary bypass for that question. I was supposed to have like a hard-coded canary on top of that I like implemented. It was supposed to do 2 memory checks, but GCC just made it the same memory location, so it just checks against itself. I love compilers.
All right, so in this case, I just pulled up the, just gonna bring up the source code real quick. The fastings example that we went over last lecture, we just allocate some chunks, free them, and then allocate them again. In this case, with the difference that I compiled with the libc version that has the T-cache. So first of all, we can look at the top here, and there's this big blue memory region that we did not allocate. This is the T-cache region. This, when you initialize the heap, when it's first initialized, libc is basically going to allocate this and use it for metadata tracking for the T-cache linked lists. So at the very top, just like with any other chunk, there's a size field. This size field basically describes how big this region is. So just like any other region, you can actually free your T-cache. I don't know why you would ever do that, but you could. And then here, this is basically 2 data structures at this point. There's one at the top, which is basically a byte map, where there's 64 bytes are used for this, where each byte represents one of these singly linked lists. And this byte map is basically used to keep track of how many chunks are in each size fast bin. So it's much easier to do for an example. So if we look at the code right now, we are currently at the freeing. Okay, this is not information. We're currently at the freeing part, I believe, so let's just type next a few times. So we just freed the first chunk. We type this. We saw that it was inserted to the T-cache bins of size 0x20. Let's type bins. We see it here. So T-cache 0x20, this was inserted. So now if we type viz and look at the T-cache data structure up here, we can see that 2 things changed. First, there's a pointer here now, And second, that there's a 1 here. So the 1 is from what I mentioned earlier, where at the beginning there's this byte map that represents the 64 regions. And in this case, we incremented this. This is here is the byte for the 0x20 size region, and we incremented it by 1 to say there's 1 entry in the 0x20 size Tcache list. So if we would free another 0x20 size chunk, this number would go up to 2. And right after this initial 64 byte, byte map here up top, there's this list here for the rest of the region, which is very similar to. Let me open the slides again real quick for this. To this arena region, where you just have a bunch of pointers in a row that signify the beginning of the different free lists. So in this case, this is for the Tcache. We have a memory region here that is big enough to house 64 pointers. So this is where the region starts. The 0x20 pointer is in this first field. The 0x30 one will be here, 0x40 here, and so on. So now this has been filled, and now the byte map up top here tells there's 1 chunk in the 0x20 size Tcache bin, and this is where the linked list starts. All right, does that make sense?
What's the size of the Tcache? Is it 0x290?
That is the size of this metadata data structure that is maintained to. This is basically like the arena, just for only the Tcache. So this 0x290 is the size of this.
So the 64 bytes for the byte map.
Yeah.
And then how many bins do you have?
64 bins, because this byte map is 1 byte for every size bin.
Okay, so added up that 80 bytes are on the counter, I think. So you get 0x240, and then
I guess there's some free space. So this would be 64 bytes, and this would be 64 times 8 bytes. It's for 8 bytes times 64 entries, so this would be 8 times 64 plus the 64 bytes. If that is less than the 0x290, I guess there's some free space. But yeah.
Where does that pointer actually point to? Is it like another location on the heap?
Yes. This is the start of the free list and would point to this region right here.
So does it point into the fast bins?
No, it points to the memory region we freed. At least it doesn't in theory. In this case, it doesn't because because it's compiled for our very modern libc version at a point where Tcache already had some security mitigations enabled. So Tcache has a weird thing that you're not going to have to worry about for your projects, but it's in this demo, so I'm just going to explain it real quick. So if you look at this pointer right here, and also this region right here, you'll see that this is not the exact address that you would be expecting. It's kind of a bit weird. Or at least the one up top here is. So this one properly points here to this one, but this one isn't. This one is not a proper pointer. The Tcache basically has a mitigation where it basically XORs the addresses that are in there with the address of the field. A bit weird to explain without, I don't want to explain it too much because you're not going to need it. Just imagine this is just like the fastman singly linked list, I guess. The reading also covers it, but that's just going to add some complexity to it. Should have probably compiled for an older Tcache version, but yeah. So if we free another chunk, let's just do that real quick. Might make a bit more sense. So now we have 2 chunks in the Tcache, the first one and the second one here. We can look at bins to see the 0x20 size Tcache bins, and we see that there are 2 entries in it now. We can look up at the bitmap here, or at the byte map, and see that the 0x20 sized region now has 2 chunks in it, and this is still the start of the singly linked list. All right, questions on this? You don't need to worry too much about how this is maintained and stuff. For our purposes, we're only going to be using the Tcache very lightly. There's a lot of complexity in the heap that we cannot fully cover in this course ever. We're only dedicating 3 to 4 lectures to this in this case, so we're going to be skipping over a lot. The reading I linked covers a bit more. I'll post another reading tonight that covers some more exploitation techniques. There's a lot to it. We can't even begin to cover all of it, so I'm just going to have to gloss over a lot of the facts, but yeah. Any question on our simplification of the Tcache here to a degree? All right. Yeah. So that's the different bins. We're going to talk about them for now. Here's the full allocation strategy. Pretty much when you execute malloc, this is what it's going to try to do. Pretty much. Also oversimplified to a degree, but more in depth than the previous ones we had. So if it's very large, you just mmap. Otherwise, you check the T-cache. If the T-cache don't have a free pointer to it, you check the fast bins. Otherwise, you check the small bins. If it's not there either, you consolidate all the fast bins into as much as you can. Then you check the unsorted bins and the large bins. And if it's not in any of there, you try to expand the top chunk. If that doesn't work, if the top chunk is fully used up, then you call the syscall to expand the heap region. There's a lot of different things it tries to do to service your allocation before it goes into the kernel. Same for the freeing strategy. If it was mmap, you just unmap it. Otherwise, you try placing it in the T-cache. If the T-cache is full, you try placing it in the fast bin. If the fast bins are full, or it's not the fast bin size, you then consolidate chunks, and then you link it into the unsorted bin again, and then you consolidate the fast bins. That's pretty much the strategies that malloc and free are going to take when you call them to figure out where it's going to get the data for, or where it's going to store it in its regions.
What do you mean when you say the T-cache is full?
So remember earlier when I said that there's the size field in the byte map? So each T-cache size can have 7 entries in it. Any more, and you then go to the fast bins or other regions.
Is there a reason you need the byte map? Why do you need the byte map?
To keep track of how many entries are already in there. Otherwise, you wouldn't know how big the linked list is. And the T-cache only holds 7 entries, so you use this map to verify that they're exactly that you can only have up to 7.
So why wouldn't you have a counter and say, I just want to know how many?
I mean, it is a counter for every chunk pretty much.
Oh, okay.
But then you'd have to store it in lines more, and with this you can have it a bit. That's just how they chose to organize it. There's a byte map where every byte represents how many chunks are in that region or in that linked list. All right. Let's get to the next set of slides on heap exploitation now. So we talked a lot about how it works. Hopefully it wasn't too confusing. I know there's a lot more to it than just put in a stack frame and then return the stack frame. So there's more to it, but we oversimplified a lot, and I hope it was mostly understandable. Let's talk about how you can break some of the assumptions that the heap allocator makes through some of the bugs we talked about. Course information project 3 is due Thursday. I'll be assigning the homework on the heap allocator today. It will be due in 1 week. So today we're going to be talking a bit about browsing the malloc source, heap exploitation basics, hooks, systems versus one gadget, has forwards, and T-cache 2. So first, let's talk a little bit about actually looking at the libc source. I have 2 links here. I'm just going to open up the first one. So you can obviously just clone it. So from this first link here, the gnu.org/software/libc is where you can basically clone the entire repo and look at it locally. For the purposes of this, I'm just going to use the source code browser. You can just look through the source code in your browser, which for a lot of things is simpler in this case. So here on the left side, you can see all the libc versions, all the way back to 2.5, all the way down to 2.0. So you have a very big, all of these different versions here, so you can very easily compare what changed from one version to the next. So look at 2.27 here in this case, because that's what you're going to be working on for your projects for the most part. And let's look at malloc, and we can go to malloc.c. All right, we can go to the malloc function here, and then you can start looking through the code. There's a lot of code there. This is the malloc function. It calls a lot of other functions as well. I'm not going to go too far in depth here. I'll pull it up again later to showcase something very specific here. But the code gets pretty complex. Like this single malloc.c file in libc is 5,600 lines of code, and that doesn't even handle the full allocation routine. So to fully read the code, understand a lot of the mitigations, you are probably going to spend a lot of time reading libc source code, which not the worst, not the best. But this is one way to let's say you try to do some technique. Say you free a pointer twice, and malloc gives you back, or the heap allocator gives you back an error, double free error. You'll get that in newer libc version. We're not dealing here, but let's just assume you might be doing a newer libc version, and that's the error you get. Then you could get this code base, grep for this error, and then check what condition caused this error. And let's say you're a researcher from 5 years ago that's trying to come up with a new exploitation technique. You get this error message, and then you can go through the code and figure out maybe there's a way that I can double free without triggering this error. And in many cases they are because libc mitigations are not very stable. We'll get back to the source code later. Let's move on to the next slides. So in the course so far, all of our exploits have been stack exploits. We had access to shellcode, to ROP, all these nice things. These are not really possible for heap exploits though. The heap, just like the stack nowadays, is NX protected, so not executable. So that eliminates shellcode pretty much. You also can't do techniques like ROP because ROP is basically reliant on jumping by popping values off the stack because ret takes values off the stack. We're dealing with a heap, so you can't execute a ROP chain. So what do we do instead? So with heap bugs, that was one of the examples we saw in last lecture as well, you oftentimes try to get a chunk out, basically get a chunk to a memory region that you shouldn't have access to. So you might try to get a chunk returned to your program that overlaps with some region that you can overwrite some passwords or some secret data or like read them out, stuff like that. So with heap exploits, what we're looking for often called something we might call write what where primitives. Basically, some bug that allows us to write anything we want anywhere in memory we want. So some ways this could be used to exploit a program. First of all, the Finney array. Who has seen that before or heard of it? Okay. So that's basically an array in memory that is located. I don't think it's using it. So the Finney array is basically is an array in memory that is initialized with null pointers. So what your program is going to do in its exit routine, so once you exit a program, it's going to check this array that may or may not be initialized and check if there's a pointer in here. So you're going to check, is this 0 or is there like some actual pointer? If there's a pointer, so you need to take this pointer and just call it. So in your exploit, what you might be able to do is if you can write anywhere in memory anything you want, you might find this array and write the address of system in there, and then you set RDI to a pointer to /bin/sh. And then when the program exits, it's going to look at this array, see that system is stored there, and it's going to call system bin/sh for you. So that's one way you could leverage that to get a shell. This is no longer very practical because one of the mitigations, I'm not sure if we talked about it, but relrow exists. And partial relrow basically makes sure that during execution, the Finney array is no longer writable. So this technique kind of fell out. There's the GOT. In project 3x3, which hopefully you've all looked at this point, you basically use a format string bug to overwrite one of the GOT entries and redirect code execution that way. If you have a write what where primitive, you can also do that using a heap bug, basically overwrite the GOT entry and then you call a system function instead. Then there's hooks. Hooks, they were recently removed from libc. Recent, I'm talking about like 1.5 years ago, so when we last did the course, it was very, very recently. So basically, let's pull up the source code again for this one. Yeah, 2.34. They were deprecated in 2.32 and then removed in 2.34.
Our job is so much harder now.
Yeah, let's find the malloc function again real quick. All right, so we're back at libc malloc here. So the very first thing malloc does here is this little check here. It reads out a hook by doing an atomic read from some memory region, and then it checks if this hook is null or not. So what it tries to do here pretty much is it checks if you have a hook set, and if so, it's going to execute the hook instead of malloc. So initially the goal of this was basically to give developers options to profile their code. I think I have a... All right, there's the link. So here's a little example of how you might be able to, how a developer might be able to use it. Let me zoom in a bit. So these hooks are basically memory regions that exist for the allocation routine. So malloc has a hook, free has a hook, and all these. Same with realloc and the other one, and cal. So what you can do is you overwrite this memory region, which is initially null, with some other pointer. So that's what this init function does. It overwrites the malloc hook pretty much. And in this case, you're going to overwrite the hook with this function here. And in this case, just like kind of a demo function. This is from the official GNU page on how you can use these hooks, where you basically call malloc and then print out the size that the malloc was called with. It also like does some restoring. For example, like it nulls them out before calling malloc. Otherwise, you are going to recursively call yourself forever the hook. But pretty much, these hooks allow developers to hook. I don't know how else to explain it. To hook these routines. So you can basically, for every single heap allocation, you can perform some instrumentation code here to basically keep track of all your allocations. You can use that to catch double freeze or just memory leaks. And back then, when this was introduced, like 10 years ago, whatever, a lot of profiling tools were based on those hooks, memory profiling tools. So Google had like a memory profiling tool, for example, that was based on these hooks. You can also use these hooks to not profile, but to, instead of using libcmalloc, to use a completely different allocator. So you can overwrite this hook with a link to your own custom allocator, and suddenly you can profile your application with your own allocator against libc allocator. So it allows people to do fun stuff like that. They've now been deprecated because there are better ways to do it. But with these hooks, they are writable during execution, otherwise you couldn't use them. So what you can do as an attacker is you overwrite these hooks with some other address, maybe with the address of system. And suddenly, instead of calling malloc, you're going to check this hook, see it's not 0, and it's going to call system instead of malloc. And finally, as to what you might be writing to one of these entries, for example, the system function is an obvious one that we've used in the past. If you can pass the pointer to /bin/sh to it, system's going to just spawn you a shell. Then there's something we haven't dealt with yet. It's called a one gadget. So basically, libc has a lot of code. It's massive code base. And somewhere in libc, there's a region of code that calls /bin/sh. So you could just get a pointer to that region and overwrite the single pointer into maybe the hook. And now when you call malloc, it's just going to jump into libc and call the system /bin/sh. You could have used that in your op chains as well, but we didn't teach you about it. Also, it's not entirely reliable. So when you do this, when you try to do this, it has some constraints. Usually, some stack regions need to be zeroed out for it to work. So if you can do ROP and do a standard ret to libc, you usually just go with that. But for heap, we don't have that amount of control often. We often can perform a single 8-byte write somewhere, and that's all we can do. And that needs to be enough to spawn a shell. So we kind of bank on these very simple ones that aren't always super reliable to spawn as our shell. So a bit more on hooks. So all of these have hooks. I didn't check, but I assume functions like printf and so on used to have hooks as well, maybe. Can probably check that by just looking at the source code browser and looking at the printf call, for example. So yeah, when malloc or free, whatever, is first executed, it checks if there's a hook or if the region's nulled out. And if there is, you execute the hook instead of malloc. This was basically just a debugging and profiling feature. And if you're in GEB, you can print the malloc hook by just typing p &__ malloc _hook. Same applies to free hook, calloc hook, realloc hook. And then you can print out the memory region here. Yeah. Any questions on this?
What does the DQ do?
Dump quad word memory. It's basically an easier way to type x/4 or x/4xg at a region. Any other questions? All right.
Wait, what's the first address in the hook?
In this case, in this example, the hook was just overwritten with some other pointer. So we print out the address of malloc hook, so usually this would be zeroed out. In this case, something's written here. So in this program, if we continued it and called malloc, it would check this hook, see that this address is here, and then it would call that.
It would reroute program code to the...
To this, yes.
Okay, interesting.
In this case, it looks like how libc used to handle malloc's initialization was that the hook was initially initialized to a function called malloc hook ini. So the first time you call malloc, it's going to call this hook instead, which initializes the malloc stuff, and then it's going to zero itself out, and then malloc's going to run as normal again.
But it doesn't do that anymore?
Now it does it in a different way.
Okay, interesting.
You can have only one hook for...
Yes. But in your hook, you can call 20 other functions if you wanted to. So you just need to redirect code execution once, and from there you do what you need to do. All right. Any other questions? Okay. So how would we be able to use system, for example, to spawn a shell? Assuming we have this write where vulnerability, let's use system first. So let's say we overwrite the hook of the malloc or the free function. Both of these take a single argument. In terms of malloc, it's the address. In terms of malloc, it's the size of the allocation you're trying to make. And for free, it's the address of the chunk you're trying to free. So how you might be able to use that to call system on /bin/sh? Well, for malloc, you just put into RDI. For both of them, pretty much into RDI, you just put the address of /bin/sh, and then the hook's going to execute. It's going to take over RDI, and it's going to call system with /bin/sh instead of calling malloc with like a size field that would be that address. So basically, if you were calling malloc, instead of passing in the size of something, you just pass in an address, and the hook's going to treat that as its first argument. Yeah.
Does that spot need to be marked as executable though? Or,
The hook?
Yeah, or like the address of bin/sh.
No.
Okay.
System needs to be executable. This is just a memory region that it accesses for a string. So the actual code that executes just the system call.
This is before calling malloc, right?
Yeah, so you overwrite the malloc code, and then we can look at the source code here that we pulled up earlier. Not this one, this one. So right here, this is the start of libc malloc. This is the function you're going to be calling. Right at the beginning, it checks for the hook. And if the hook exists, it's just going to call the hook instead and return that instead of continuing with the rest of the malloc routine.
The malloc has one argument, right? So
Yes.
isn't that going to be argument?
Yeah.
Overwritten, so then our string is one.
No, so when you call malloc, so you do the call to malloc, and then instead of passing in the size of 0x20 or whatever, you just pass in the address of /bin/sh.
The size T is 32 bytes or 64?
Or what? Oh, the size field?
Size T.
64.
Okay.
Size T on a 64-bit system would be 64, and on a 32-bit system, 32. Okay. Another way is the one gadget. This is done using, usually you just use a tool for it. The tool is called one gadget, very easy. So you basically run this tool onto the libc, and that's going to print out some addresses that contain this one gadget. So it's pretty much always going to print out 3 addresses for you. In this case, it uses, actually let's use execv to spawn a shell instead of system, but it just executes, but that one works too pretty much for this. But it always has some constraints. So it would tell you, if you call this address, RSP and 0xf needs to be null, and RCX needs to be null. If you want to try this one, then RSP plus 0x40, what's stored there needs to be null. And for the last one, RSP plus 0x70 would have to be null. So there's some constraints on them. So there's a chance that your program does not meet those constraints, and you do not have the power to meet them. So in that case, you wouldn't be able to use the one gadget. But yeah, otherwise it just works. In your project, I think we have 2 heap challenges that use 2 of those techniques. One of them is going to have you using the system technique, and another one the one gadget. In the one where you have to use the one gadget, we're going to give you a libc and the output of the one gadget tool on the libc because the tool does not exist on EdLab. If you're on your own device, you can very easily install it. I think it's a Ruby script that you install, like gem install one gadget. But yeah, you can just Google for it, or GitHub repo, and yeah.
Wait, can we clone the repo and then just mark this?
I think you need to do a gem install. Just look at their installation instructions.
The project, would it be statically compiled?
No, but we'll be giving you libcs that are linked into the project. So basically, there are ways to patch in custom libc versions. This is the easiest. There are multiple ways. This is the easiest way that we're going to be using. So in projects 4 and 5, some of the challenges will ship with custom libc versions. So we'll give you both a challenge binary and a libc version. Those are only custom in the way, like we didn't modify them, but they're an older libc version. I believe it's 2.27 and 2.28 you'll be working with. And those just have a little bit less mitigations than current libc versions have, because current ones are going to be much harder to work with. So basically, these binaries will already be patched to basically use these local libc versions that we're giving you instead of your system's one. If you want to compile arbitrary programs and test them against older libc versions, you can use a program called patch.elf to basically set the interpreter and the libc to a custom one and use that instead. All right. Any questions on this so far? It will basically keep setup and how you might approach these exploits. Then let's talk about two more specific exploitation techniques. So with Heap, there are a lot of known techniques. The history of this paper here, the frac link here, I'm going to be uploading that onto Moodle as well. This was basically the first time heap exploitation was publicly documented in such a way. It was published in 2005, and it basically theoretically describes a lot of techniques that can be used against a lot of those bugs. In this case, it describes 6 different techniques. We're only going to be covering 2 different ones in this class. Nowadays, there's well over 60 different techniques, and if you want to play CTFs at a high level, you kind of got to know a lot of them for binary exploitation, which is not fun and would not recommend. So I'm going to be covering like some very simple ones, and the more difficult ones, if you're interested, you can always research them. But oftentimes, they're not super relevant. So we're going to be covering here is the House of Force. That's the first one we'll be covering. Before we do this, let's do a small demonstration on the hooks. So we have this demo binary here. So there's the code for it. The main function basically prints out a menu. This menu gives you a few options. If you type in 1, allocate a chunk, 2, free a chunk, 3, edit a chunk, and 4, exit. And then it parses out a number from this, and then calls a function based on this. The allocated chunk basically gets the size from you and then allocates a chunk using malloc here, and stores it in this data array here. The free chunk, same thing, it asks you for an index, and it's going to reference this data array and just free this buffer. And the edit chunk just, once again, asks you for an index. Once you give it to it, it's just going to overwrite some data there. So it's basically a small wrapper to just work with some malloc routines and explore some of these bugs. Let's run it real quick. All right, so let's start by allocating a chunk. So we can now see that this chunk is allocated here. So let's do a very small damage overwriting the malloc hook. So we can print out the malloc hook. We can print out the data that is stored there. And we can see that it's currently entirely zeroed out. So what if we, however, overwrite it? Now if we print it out again, we see that we overwrote the malloc hook pointer with zeros for 1 for 1 for 1, 8 8s. So if I were to now continue and then use option 1 to allocate another chunk, what would you expect to happen? Based on what we've been talking about. Yes, segfault. So we continue. We ask to allocate a chunk. We give it any size we want, say 0 to 30. And we're going to be segfaulting on a jump. Zooming in a lot. On a jump to 0 for 1 for 1 for 1. So malloc read the hook, tried executing it, and we gave it an invalid value, and it segfaulted. So that's basically what you're going to be trying to do in your exploits, just overwrite it through some bug and give it a valid address that might spawn you a shell. So the House of Force technique is the first technique we're going to be talking about on how to accomplish this. This technique was first released in 2005. Just to put some perspective onto how little libc and in general developers often care about security, this technique was first discovered in 2005 and was not mitigated until 2019. Yeah, and that's pretty much. So heap vulnerabilities have an interesting history, more so than ROP even, where there's a lot of mitigations. That's why there's so many different techniques. Basically, very often one of these bugs or techniques was developed, discovered, whatever, the libc developers would make some very small mitigation for it. Maybe you find a way to corrupt some pointer, and they realize, okay, if I add a size check here, it's going to kill off this technique. But then exploit developers realized, what if I just change this 1 byte in my payload that's going to bypass their mitigation, and a new technique will spawn. And this kind of went on for a long time, and it's still going on, and libc kind of just keeps adding a bunch of tiny mitigations that kill off a very specific technique. Then the exploit developer comes up with a different technique that bypasses that mitigation, and now we're left with like 40, 50 different individual mitigations and a bunch of different exploitation techniques. It's a big mess, and yeah. There are better ways to do allocations that are handled in a secure way, but you usually give up some form of performance for it, and libc and generally C developers do not want that. So the first technique, House of Force, first discovered in 2005. The goal of this is to return an arbitrary pointer for malloc. So what would that allow you to do? Let's say your program calls malloc, and you can decide what pointer you get back. What would you do with it? What pointer would you maybe return, and what could you do with it based on what we've discussed so far?
An address to defeat ASLR.
Yeah, that would be a possibility. Although not that useful in this case. Let's say you call x is equal to malloc. Let's say this is what's happening in your program, and you could decide what address this returns to you. You're still not really going to know the address of x as the person writing this exploit. What else could you do though? Assume you later in the program somewhere it's going to do a mem copy and like write some data to x that you control. This might be like a password manager where it allocates a region and then like writes your name there. And I ask you for your name and then like writes the name there, your username. Assuming you can decide where it's going to write this to. How would that look?
The malloc hook.
Yeah, exactly. That's one thing you could do. So if you can control what malloc returns, you could return the address of the malloc hook. Then later when it's writing to it, you're overwriting the malloc hook instead of some proper memory region that is designated to the heap region. So that's what the House of Force technique relies on.
Wait, so how do you choose what malloc returns? Or rather, how do you make it?
And that is what the technique is going to come down to.
Oh.
So this technique is basically relying on a bug that edits the top chunk size field. So if you remember looking at programs, if we type in viz, we have the top chunk here at the bottom, which has a size field. So this size field then tells you how much room you have left before you need to call syscall to allocate a bigger region. What do you think could happen if you could overwrite this size field and set it to a very, very large value? Anyone want to take a guess? Yeah.
Would it allow you to allocate in free from memory that you shouldn't be able to allocate or free?
Yeah, exactly. So if this size field, if you just tell it it's infinitely big, let's say you just put in -1 and it's going to be 0xFFF, whatever, that's going to be treated as unsigned integer, so basically billions of bytes. You can just keep making allocations. It's never going to go into the kernel to ask for more memory, and eventually just going to be overwriting existing memory regions because you think you're allowed to do that. So that's what this technique is reliant on. So you have some form of bug that allows you to overwrite this pointer. The simplest bug that might be, let's say you allocate this chunk and there's a heap buffer overflow, and you can go out of bounds of this chunk and you might be able to just overwrite this. Yeah.
Why would that not segfault first? Because page is unmapped or something like that. You let it just start writing to basically random.
It would only segfault if you're actually writing to it, not if you're just doing allocation, because allocations don't initialize anything except the size field at the beginning. So let's say this is your address space, and this is your heap region, and this is some other region, and let's say this is unmapped. Let's say you can make a massive allocation that spans this entire area. The size field will be written here at the beginning somewhere in like still valid region, and in this entire region, you're returning to your program as allocated memory, but you're never writing to it, so it's never going to cause a protection fault. And then the region goes up to here, and maybe you just write to this one region that is allocated, but maybe to libc. And maybe it's allocated to libc, so you're overwriting libc code regions or whatever. So that is the basis of this technique. Yeah. So you overwrite the size field of the top chunk, and then you do a very, very large allocation, as described here, that basically goes right before where you want to write, and that moves the top chunk up to that location. And then the next allocation you do is going to overlap with the region you want. So let's go back to this memory region example here. This is where the heap is. And let's say right here in memory, and this line here, that's where the malloc hook is located. And this is what you're trying to overwrite. So we start by overwriting the top chunk size field we set it to -1, so it's infinitely big pretty much for our cases. And then we do a massive allocation that goes right before this malloc hook. It's not going to cause a segfault because we're not writing to anything to this unmapped region, and we're right before this. And then we could do another allocation. And now this allocation, assuming none of the bins are filled, is going to try to use the top chunk. The top chunk still has bytes left. So it's going to check here. The top chunk is currently here. Let's do another allocation. And then it's going to allocate this region of memory for you. And then you can overwrite the top chunk. Then you can overwrite the malloc that is located here. And your top chunk basically just goes there. Questions on this? Yeah.
What do you do if the bins are filled? Like, can you still do that, or?
Not directly, then you'd have to empty out the bins by making a few allocations first maybe, or using a different size field that isn't in the bins.
To do this, do we need to know where the malloc is?
Yes. So that's malloc is stored somewhere in the libc memory area, so you would need an ASLR link for this.
You pretty much need a malloc in a loop that you can control how many times it loops and
Not necessarily how many times, you need at least 2 allocations for this. But you do need to control the size field for this.
size.
Yeah. So maybe an application asks you how long is your username, and then you're going to tell the length, and then it's going to allocate that, and then you're going to write to that field, your username to there. That might be, for example, one of those bugs that could cause this. So it's not like with heap bugs, there's a very specific amount of control that every bug and every application is going to give you, and different techniques are going to apply to different bugs. So this house of force technique is not universally applicable to every heap overflow, just to a very specific subset that give you that amount of control that you have. Otherwise, you're going to have to go to a different technique. That's also why there are so many, not just the mitigations, also that the amount of control you get is going to depend a lot on the application, and is a lot more complex often than just having a buffer overflow. All right. So yeah, this technique, as mentioned earlier, it's fully mitigated in glibc 2.29, which was released in 2019, even though this technique was released in 2005. It took them forever. 2.28 actually has a small mitigation implemented for it. That's when they first looked at it. This mitigation basically just checked that this top chunk size field is not extremely large, but it was still bypassable because it just checked that it wasn't like 2 to the power 64. So if you make the size like 2 to the power 30, you might not have this massive overflow, but you can still allocate 4 billion bytes. And that made it a little bit harder in some cases, but it didn't mitigate it, and then in 2.29 they properly mitigated it. So yeah, so this is our basic exploitation strategy now. We're going to be dealing with 2.27, so you can happily overwrite it with 2 to the power 64 and it's not going to complain. So what we're going to be doing in our exploit is overwriting the top chunk size field with -1. That's going to set it to this very large value if treated in an unsigned manner. Next, we're going to calculate the size of our allocation. Let's talk about type B first. That's the easier one. So assuming we have this memory region here and the malloc is here, what we need to do is get the address of the malloc. Let's say it's 0x1234. Then we're going to subtract 0x20 from it. And then we're going to subtract the current address of the top chunk, which would be here. And this basically, let's say this is your entire memory area. So you go back 0x20, and then you subtract this area as well. And then you basically get this allocation size that you need to bridge to get right before this malloc. Does that make sense? The math of this, yeah.
So the 0x20 is the size of the malloc?
No, 0x20 is just like to be a little bit before the malloc. It could also be 0x10 and 0x30, whatever. You're just trying to not overlap it, because you're not trying to overlap it in this allocation. You want to be right before it, pretty much. So your next allocation that overlaps it. So it doesn't have to be exactly 0x20, it's just what's on the slide in this case. But you're basically trying to be right before it, so you basically do the calculation of how many bytes you need to bridge to get from here to right before the malloc. So where the top chunk is right now, to move the top chunk right before the hook. So you calculate the size for the allocation, then you do the initial allocation that bridges this entire gap up to right here, and then you do another small allocation that's not going to be massive. So this is going to be 0x30 bytes maybe, that then overlaps this hook, and you get that back, and then you can overwrite the hook. That is the basic idea. There's also option A. I don't think you're going to have to do that in your project, but memory is weird. So what if your top chunk is here, but you want to overwrite something that is here before it in memory? So another thing you can do is do an allocation that's large enough to wrap around the entire virtual address space, and then it's going to go back to the beginning. So that's something else you can do. The calculation for that looks a little bit different. You calculate 2 to the power of 64 minus the address of the top chunk, plus where you want to be, and then minus 0x20, and then you're going to end up right before it as well. Just this case making an allocation that's big enough to wrap the entire virtual address space and go back to the beginning. I don't think you're going to have to do that. If you think a bit about it, it's going to make sense though why this formula works for it to think about the size of your allocation. But yeah, before we move on to a demo of this, does this make sense in theory? All right, so let's open up a small demo of this. All right. So we're going to be running our demo binary again, the one that basically allows us to do whatever we want. So let's allocate a chunk, negative size 0x10. If you look at the heap mapping now, we can see that this chunk is right before the top chunk. The demo application in this case is very vulnerable to pretty much everything, double freeze, heap overflows, whatever, so we can just play around with it. So we're going to continue, and we're going to edit the chunk at index 0, and let's just give it some data. Type viz again, and we can see that we overwrote the data with a bunch of A's, including the top chunk size field in this case. We want to have it set to -1, and I can't type 0xFFFF that easily without using Pwn tools, so I'm just going to set it through GDB in this case. If you have Pwn tools, you could have just used that. All right, so we did some GDB hacking here, and now it's set to -1 if treated as an unsigned value. So that's our first step. Looking back at the slides, we overwrote the top chunk with -1. So now we got to calculate the size of our allocation. So let's open up Python prompt real quick. All right. Anyone remember what the first thing was we needed?
Target size.
The target's address, yes. So let's say we want to overwrite the malloc. So we can go print address of the malloc. And that is at this address here. All right. What next?
We just subtracted with the 0x20.
And the last value we need?
Top.
Yeah. And lastly, the top trunk address. So we can just type in top trunk. And we get this address here. Print out as a hex value. So that's the size of the allocation we need to make to bridge the gap between where the top chunk is at currently to be right before the malloc. So let's do that.
Sorry to interrupt. Does this have ASLR already in it or not? Or does that not affect anything?
ASLR is there, but we're doing just a demo here, so I'm just gonna use the GDB values.
Okay.
If you were doing that and like writing your exploit by hand, you would need to figure out get an ASLR leak, for example, similar to like the other things we've been doing. Just how you and you would also need a heap leak. So heap is also affected by ASLR, but in this case you're going to need 2 leaks because the heap is at a different. Oops, open up the map real quick to show this out a bit better. Let's zoom out a bit and hope it's still visible. All right, this is probably not great for you to read anymore this size, but here's the heap, the yellow region here, and libc is here. So they're both yeah, here. No, that's the linker. Here's libc. So these both regions are both affected by ASLR, but the base addresses are randomized independently from each other. So for this technique, you need a heap leak that exposes the address of the top chunk, and a libc leak that exposes the address of the malloc, for example. So to do this technique, you'd need 2 address leaks. All right. So
Actually, never mind.
All right. Any other questions? Okay. So we have this size, and we just discussed that this is the allocation size we need to do to bridge this gap between the top chunk and the malloc. So let's use our demo application that lets us do arbitrary size allocations to do that. We allocate a chunk, give it this size that we just calculated, and it happily allocated it for us. Let's look where the top chunk is right now. If you look at the address and the size field, these do not look correct at all. the address is no longer in the heap region, it is now right before the malloc hook. So we can print out the malloc hook. Zoom in a bit again. And you can see that this is basically right before this. So our next allocation, if we're going to make it of size 0x20 maybe, it's going to start then overlap with the malloc hook, and we can overwrite the malloc hook. So let's do that. Continue the program, allocate another chunk. Let's say size 0x40. Oh, so that size 0x. Yeah, that doesn't matter at all. So we did another allocation. And now let's edit that allocation. I believe that should be index 2. Yeah. And let's just give it a bunch of keys. Let's break again. And if we print out the data at the malloc hook now, we can see that we overwrote the malloc hook with those values. So now we could instead overwrite the malloc hook with the address of system or the address of one gadget, and that would be enough to spawn a shell.
The malloc hook is just the first 8.
Yeah, the first 8 bytes here. I believe the next one is the pre-hook, and so on. I'm not sure about the exact order, but all these hooks are in the same region pretty much. And I believe this is right after the arena. So there's the arena in memory with all their pointers, and then there's the different hooks and stuff. They're all in the same memory area. Questions on the House of Force technique before we move on to the next one?
Do you also need a leak for system, or can you get that from having this leak for the malloc address?
System you get based on the libc leak. So you need a libc leak and a heap leak, and system you can calculate based on the libc leak.
Okay.
All right.
Does it heap have like a little section that if you write to, it just crashes everything? Or something like that. But you allocate over it, and it doesn't matter because you're not writing to it.
Yeah.
Gotcha.
I mean, if you write to an area that isn't mapped, you're going to sec fault instantly, for example. So if we were to make this massive allocation and start writing bytes to the middle of it to regions that aren't mapped, we're going to sec fault, for example. But otherwise, if you're not writing to it, if you're just allocating just returns a single pointer. By allocating, you don't actually do anything.
Can you show us how you did the top chunk to the FFF?
In GDB, you mean?
Yeah.
In GDB, you just do.
Because
What was that? Merge this. In your exploits, you do it by running the program through a buffer overflow, for example, through a heap buffer overflow. In this case, I just used GDB to do it in a more easy way for the demo, but yeah. You can't open up GDB and do it in GDB for your projects, but that's an easy way out. You can test some things out. Other questions? All right. Let's move on to the next technique then. This one is arguably easier. So this one's called the T-cache dupe. In this case, we're going to be dealing with the T-cache. The goal is once again allocate a chunk at an arbitrary address. There are multiple ways to exploit this. Popular way is a double free. So this exploit, this technique you can do through multiple different vulnerabilities. It's more of a general strategy than like the more specific one of the last one. So doing it with a double free, the general idea would be to free this same chunk twice, to link it into the T-cache list twice. Then your next two allocations will be returning the exact same chunk. So you allocate once, and then you can overwrite the metadata, and then you allocate again, and yeah, that's like the demo we did last class at some point. I'll do it again in a second. Let's just do the demo for this, it's probably easier. So we once again have our demo program. Let's allocate a chunk, and then let's free it once, and then let's free it twice. We didn't have any double free checks, so we just freed it twice. Now look at the bins, and we can see that the same chunk is linked into the 0x20 size T-cache bin twice. Also type viz. And we can see that this chunk's in the T-cache bin twice. We can look up at the T-cache list all the way up here. And the 0x20 size chunk also has, the byte map says that it's been mapped. That two chunks are in this T-cache list. So now what happens if we allocate one chunk, and then we edit this chunk. Let's pass in some A's. Type viz again. And now we can see that that these A's are now in the T cache as well. So now we can make another allocation. It's going to return the same chunk again. And then the third allocation is going to return whatever's at this address here, what we just overwrote it with. That's basically the same demo we did in the first lecture. We're basically just overwriting the FD pointer with a different address to basically add it to the list. Instead of it being null, we're setting it to some value, and that allows us to return an arbitrary chunk when doing an allocation from the T cache. Questions on this technique? So this technique is very generalized. Pretty much most of the heap bugs we've covered, you could in theory use to do this attack. Let's say you have a few chunks here. Say this is chunk 1. In a different color maybe. Then right underneath it here is chunk 2. So let's say you have a heap overflow in this chunk. So let's say you free this chunk. So this is going to be overwritten with the FD pointer, and this will then be linked into the T cache list for, let's say, size 0x20. So then this now contains a pointer to this chunk, and this has the FD pointer in here now. So now we have a heap overflow in this chunk, so we write out of bounds, and we can overwrite this FD with the address of the malloc, for example. And now when we do 2 allocations from this TCAP from size 0x20, the second one will now be returning the malloc memory region. Same with the double free as we just did there. You can also use a use after free where you free it and then you overwrite it. Basically all heap bugs we've talked about pretty much can be used to leverage this technique. So this one is a very generally applicable one. Basically just linking a chunk into the T-cache twice, or basically having some way to overwrite the FD pointer of a T-cache bin. That's all you need in this case. Does that make sense? Yeah.
So is the fact that this is so general, does that mean it's still being used right now?
Yeah, pretty much. There are some mitigations in place. That's where earlier in the lecture when I talked about the T-cache, remember when I said that the FD pointer is Zord now? So the FD pointer you can no longer directly overwrite. You need a heap leak now as well because the address that is stored in the T-cache bin and newer libc versions is stored against the address of the chunk pretty much. So now it's like that's a light protection. If you have a heap leak, it's bypassed, but you do now need a heap leak as well for it. So it's basically just piling up mitigations and mitigations that always have some form of bypass, but just makes it harder. All right. Anything else? Because this pretty much concludes the heap topics we're going to be covering in the course this year. So next week we're going to be doing our lab on this, where we'll be going through some more in-depth, where you guys are going to be writing an exploit for, I believe, the House of Force technique. So we're going to be going a bit more in-depth into those techniques. In previous years, we did try to talk about some real-world vulnerabilities. Who here heard about the pseudo bug? You were there. So that's a bug that happened, I believe, was either last year or 1.5 years ago, like very, very recently, in the past 2 years sometime, where a research team found a bug in sudo. It was a heap bug where you could basically pass sudo command line parameter that allowed an unprivileged user to get a root shell on the device. That was a pretty major bug, and that was caused by a heap exploit in this case. If you're interested, you should read up on it. It was a pretty interesting exploit. They gave some talks on it as well. You can watch those instead of reading, maybe a bit more comfortable. But that kind of if you look at that one, that's going to expose a little bit more how modern heap exploitation looks to a degree than what we're covering here, because these are techniques from 2005. But yeah, they're out of scope for this course in general, I would say, but look at them, they're interesting. But yeah. Any other questions at this point?
This isn't really about what we're learning, but are the cybersecurity talks like streamed or recorded?
Of the club?
Yeah.
No, we get lazy.
We used to do it. But yeah, not anymore, I guess.
We can stream one this week, I think, if we get it running, but we haven't been able to get it running on all our computers at once.
TLDR, we might.
We can send the slides, worst case scenario.
I'll upload the slides for today's lecture, the demo binary, and the PDF to the track paper that I linked here onto Moodle later today, and the quiz will be released as well. That one, or the homework, it should be pretty easy. Shouldn't take too long, like 30 minutes probably. Yeah, that's all for today.